Hello everyone, good morning. Welcome to the Theory of Vibration Aeroelastic Lecture Series. Today we are going to see the aeroelastic problems on aerospace engineering. Welcome to this technical presentation on aeroelastic problems, one of the most important topic in aerospace engineering. In modern aircraft design, understanding how structure behavior under aerodynamic forces is critical for safety, efficiency, and performance. Today, we will explore the causes, classifications, solutions, and real-world case study of aeroelastic problem using a design thinking approach. Let us begin this exciting learning journey. So, in aeroelastic study of the interaction between aerodynamic force, elastic force, and inertial force acting on aircraft structures, the aerodynamic forces comes from airflow pressure and velocity around the wing. Elastic forces are related to structures, stiffness, and deformation. So the initial force arises due to the mass and acceleration. When these three forces interaction improperly, the structure instability may occur. That is why aeroelastic is a key discipline in aircraft design. So this is a triangle which indicates the interaction between aerodynamic force, inertia force, and elastic force. Next, the aeroelastic problems are mainly classified into two categories, the static and dynamic problems. And static problem includes divergence, that is to see instability at a higher speed. Control reversal occurs when the control surface loses its effectiveness, whereas in dynamic aeroelastic problems, flutter and buffeting plays a main role. A flutter, a self-exciting dangerous vibration, whereas buffeting, which is forced oscillation due to the turbulence created by the airflow. Static problems depends on stiffness, while dynamic problem depends on time-varying motion. Now coming to the design thinking process, first we understand the problem deeply. Engineering study how aerodynamics, elastic and inertia force interacting with each other, where the critical problem includes flight speed, Mach number, structural stiffness, flexural rigidity, and torsional rigidity, also damping characteristics of the material. The proper understanding helps us to engineer to predict failure before failure is happening. Now coming to the ideal section, now we brainstorm possible engineering solution. Common aeroelastic solution includes increasing structural stiffness, redistributing mass and center of gravity, which installing active flutter control systems, also modifying wing shapes and aerodynamics. Every solution must balance cost, weight, performance, and aircraft safety. This stages transforms problem into innovation opportunities. Now coming to the prototype model, once the idea are selected, engineers create models and simulation, they are using popular tools like finite element analysis for structural behavior, CFD analysis for flow simulation, and finally coming to the testing on using wind tunnel testing for the experiment validation. Industry software includes ANSYS, Nastron, Abacus, and Fluence. These tools help engineers reduce to risk before the actual manufacturing. Now coming to the mind mapping, let us assume the summarizing between aeroelastic problems using mind mapping concept at the center in the aeroelastic problem, which includes static and dynamic problems, causes, aerodynamic effect, elastic effect, and inertia effect, which affects vibration, instability, failures. Solution gives by raising stiffness and control system, which is the greater application in aircraft, airplanes, bridges, wind turbines. This shows how aeroelastic phenomena helps and applied beyond the aviation sector. Now coming to the real world example gives us the clear understanding of one of the famous historical example is the Tacoma Narrow Bridge failure in 1940. The bridge collapsed due to flutter induced torsional oscillation. This event changes structural engine forever. How the modern aircraft now use the active flutter suspension system structural optimization use the real-time monitoring sensors. So today's aircraft is highly safety and the longer surface. Now coming to the testing phase is the final stage of this phenomena. Methods include internal testing, flight testing, numerical simulation, evaluation. Criteria includes flutter speed greater than 1.15 times maximum operating speed, the damping ratio above safety limit, the frequency safety margins. Only after successful testing can aircraft be certified as a safe model. Finally, the testing in the final stage methods includes visual testing also helps to understand aeroelastic phenomena safety performance, which gives the balance aerodynamics, elastic and inertial forces. Further direction, the active control system for flutter suspension and AI-driven optimization technique can be used in the aircraft to understanding the aeroelastic phenomena. So this is how we are understanding the basic aeroelastic phenomena in aircraft. Thank you. We'll see in the next class.